So here we are once again, new topic, 12.6, reaction mechanisms. And again, you're watching the video while, well, not while I'm staring at this board in a room by myself, but that's what I'm doing while I'm making the video. Okay, what is a mechanism? So we're going to talk about reaction mechanisms. And mechanisms are a series of elementary steps that combine to show the path molecules take from reactants to products in a chemical reaction. Let's erase all of that now. Okay. By the way, you should have a sheet with all the terminology for different vocabulary words I'm going to use today and that we're using throughout this chapter. So get that sheet out if you don't already have it out. In these mechanisms, which you'll see in a little while, a short while, we have something called elementary steps. Elementary steps. Elementary steps are reactions where a few, 1, 2, or 3 particles come together and react to form products. And these elementary steps represent single collisions that occur in a reaction pathway. So up till now, we've only seen reactions as this whole huge reaction. Now we're going to take that reaction and take it into little steps of what's really happening. Because if we have 5 molecules forming 2 molecules, those 5 molecules don't just magically come together and form the 2 molecules. They go through a series of steps. And the series of steps are the mechanism. Whoa. Okay. Rules for mechanisms. We have a whole bunch of rules. They're all up here. I'm not going to read them. You might want to pause and read this. I'm just going to move forward. So hopefully you paused and read through all of that. But I do want to point out, I just took a, I put on the screen the terminology for Chapter 12. You should have printed this out already. And real quick, catalyst is in there, as is intermediate. So again, you might want to look at your sheets. We've got mechanisms in there, several different items in there that we will be going over today. So now we're going to return back to mechanisms, and we're going to do an example. So again, pause. Oh my goodness, it's really acting up on me. Pause if you haven't taken the time to read through this. But here we go with our examples. So we have a reaction right here. This is the reaction we're trying to get to. And we have a proposed mechanism right here. We want to know, is the mechanism consistent with the reaction? So let's see what we need to check. First, we have to check if the steps in the mechanism add up to the overall reaction. We're going to check whether or not that is true. So we're going to add up the steps in the reaction. Hold on. I rewrote the 2 steps, and let's see if we can cancel anything out. So if I look in here, hopefully you see that the NO3 cancels out, and I have an extra NO2 in there. And does that give me the final reaction? NO2 plus CO makes an NO and a CO2. Yes, when I add up my 2 steps in the mechanism, I get my overall reaction. Now, this mechanism, what does it really mean? So, oh, goodness, don't look at that. Before we do that, let's take a peek at this. When we add the 2 reactions together and we get the overall reaction, these 2 together make the overall reaction. Let's check, do we have any catalysts or intermediates in here? So looking at this, I'm going to pause. I notice that there are some things in the steps that didn't appear in the overall reaction. This NO3, it's in my steps, but not in the reaction. So I look and I see, I'm trying to determine, do I have any intermediates or catalysts? So I know NO3 is one or the other, so I'm going to look at my mechanism information. What does it say? We see an intermediate is a chemical that appears for the first time as a product and later as a reactant. Let's see what happened here. So NO3 is appearing for the first time as a product and later as a reactant. Looks to me like NO3 is an intermediate. NO3 is an intermediate. Now, do I have any catalysts? Does anything appear for the first time as a reactant and later as a product? Now, some students will make this mistake. I'll tell you up front, there are no catalysts in here. But some students make the mistake here that this NO2 got canceled and it appeared for the first time as a reactant, later as a product. So that must be a catalyst. But no, because NO2 is in the overall reaction, it's not an intermediate or a catalyst. Even though I was able to cancel out an NO2 from my steps, since it is in the overall reaction right there, it is not an intermediate or a catalyst because neither intermediates or catalysts appear in the reaction. This is the same reaction we were just looking at, but you're now looking at pictorially what are these molecules and what's going on. What we're saying is that we have two molecules that come together and they form some products. And then one of those products comes together with another one of the reactants and we form some new products. So there are two bimolecular steps. Bimolecular is in your terminology sheet. Look it up right now. Hopefully you've looked it up and you see a bimolecular step is an elementary step in a reaction mechanism that involves the collision of two particles. So we have step 1 and step 2. Step 1, right here. Two molecules come together and react. Step 2, again, two molecules come together and react. When we add up those two steps, we get the overall reaction back. We have two bimolecular collisions that cause this overall reaction to occur. So in the reaction, it's not that an NO2 and a CO collide to form the products. According to our mechanism, we don't know if this mechanism is correct or not. Mechanisms are proposed. So we've shown that the mechanism is consistent with the overall reaction. When we add up the mechanism, we do get back the overall reaction. So far, the mechanism is consistent with the reaction. Now we want to check, is the mechanism consistent with the experimental rate law? So someone runs an experiment. We've done this. We know how to run these experiments. And we find the rate law. And we want to check if this reaction mechanism that's proposed is consistent with the rate law that's experimentally determined. Now, we were told that the first step was the slow step because we're told that right here. You're always given whether the steps are slow or fast. So right here we are given that step 1 is the slow step. Pause. Ooh. So I'm going back here to step 1 is the slow step. And according to our rules, rule 2, right here. The rate determining step gives you the rate law for the overall reaction. And we just use the coefficients in the step of the mechanism that is the slow step, and we put those coefficients as the exponents. So let's look. Okay. So our slow step, right here, step 1 with slow step, that means we have 1 NO2 times 1 NO2 times K. right here. So the rate will be K times the coefficient NO2 raised to the X, which was 1, times NO2 raised to the Y if we were thinking of NO2 as two different things. But again, it would be 1 because the coefficient was 1 in the slow step. And that is equal to K NO2 squared, because NO2 times NO2 is NO2 squared. So we find that this is consistent with the experimental rate law. Yes, the mechanism is consistent with the rate law. Very important point here now, though. Caveat. We cannot prove that the mechanism that we've proposed is correct. We just can't prove it at all. We have shown that the mechanism is consistent with the reaction and the rate law, but we have not proved it's correct. What we can do is eliminate proposed mechanisms if they don't satisfy the rate law. So, new problem, example 2. We have our reaction right here, and we want to know which mechanism, A or B, is consistent with data that produces the differential rate law right here. So we're going to check. We'll check A, and according to our rules, the rate is based on the slow step. Well, that is the only step, it is the slow step. Rate is K times the concentration of a chemical raised to its coefficient. And the coefficients on all of these are 1. This would equal K times ClO 1 minus cubed. That does not equal the rate law. Does not equal the rate law. So, it's not A. Mechanism A is totally inconsistent, doesn't work. So, let's check B. Here's our slow step. B. And you can try this on your own if you'd like. Go ahead and pause if you know what's going on now. Rate is K. The reactant in the slow step raised to its coefficient. ClO 1 minus to the first power. ClO 1 minus to the first power, which is K. ClO 1 minus squared. And that is the rate law. Right there. I have not proved that this mechanism is correct, but I have proved that it is consistent with the experimental rate law. Okay, so now we're going to have a couple more questions about this experiment. All right, so I'm recording. Okay, so here's my reaction. And I'm going to add those together. And first, let's see if there's anything that I can cancel out. I notice this ClO2 1 minus will cancel out. I think that's it. Okay, so I end up with 3 ClO 1 minuses, making a ClO3 1 minus and 2 Cl 1 minuses. And look at that. That's what we got. That's what we were looking for. So this mechanism is consistent with the reaction. And as for intermediates, well, the chlorite, ClO2 1 minus is chlorite. The chlorite appeared for the first time as a product and then got used up later as a reactant. So the chlorite is an intermediate. And then to explain, we would have to write chlorite is an intermediate because it appears as a product in step 1 and is later used up in step 2. Okay, going on to number 3. We have a proposed mechanism for this reaction. And step 2 is slow, so I know this is so easy. The rate is going to be K, concentration of O to the 1 because the coefficient is 1, concentration of, that's ozone, to the 1 because the coefficient is 1. Okay, I'm all done, right? No, we have a problem. What's our problem? We do have one. O is an intermediate. It's not allowed to be in the rate law. If you look at your rules about rate laws, one of the issues is we are not allowed to have intermediates in the rate law. So we have a trick to get rid of the intermediate. And you have to remember something from last year in order to do this trick. I'm also going to write a few things up here. Okay, so I have added a few things in here. And we're going to extend the page a little bit, come back down. Okay, we're going to pause. And here we go again. Okay, I was having a little computer trouble there. So I've put in these little K's here, and those are rate constants. F stands for a forward reaction. R stands for a reverse reaction. So I have K1, because it's step 1, for the forward reaction, going forward. And then I have K1, reaction 1, for the reverse reaction. That's for this reaction going in the reverse direction. This K1R goes with the step 1 reaction in the reverse direction. This K2F stands for the step 2 rate constant in the forward direction. Now, based on rate laws, for step 1, I know that the rate for the forward reaction is equal to K1 forward times the concentration of O3 raised to the first power, and the rate in the reverse direction, still on step 1, so the reverse rate will be K1R times the concentration of O2 times the concentration of O. Because if this reaction is going in the reverse direction, these are considered my reactants. And according to my mechanism rules, the rate of a reaction is K times the reactants raised to the power of their coefficients. So if I reverse the reaction, these two chemicals are reacting. Okay, so now I'm told this is fast and reversible in step 1. What that means, if something is fast and reversible, it means that rate forward is equal to rate reverse. You have to know that whenever you have a fast reversible reaction, the forward rate is equivalent to the reverse rate. So I'm going to just plug in what I have. My rate forward is K1 forward O3. My rate reverse right there, K1 reverse O2 O. Now, something magical can happen here. I know that my rate, based on the slow step, is this right here. Oh, I'm going to fix this. I'm going to call this K2F. You don't normally have to write in these K1R, K1Fs, K2Fs, but since I've specified the K's here and here, I'm going to use those values when I solve for my rate law. Okay, so let's see. I needed to get rid of the O from my rate law for the slow step because we're not allowed to have intermediates. So I need to get rid of this O. I solve for O, and then I plug it in. I'm going to solve first. All right, all I've done here is solved this equation right here. I solved it, isolated oxygen, and now I am going to plug this value for oxygen, all of this. I'm going to use substitution and substitute it right into oxygen right there. Okay, I did it. I plugged it in. If you wanted to pause, you could pause before you look at this. Try to solve it on your own. We substituted oxygen into the rate law, and I get this. That is my rate law. Now, you have a choice. You can leave this rate law as is, showing all of these K's, the K2F, K1F over K1R. Or, note, these are all just constants. We have a constant times a constant. They're different constants over another constant. And if I have three constants mathematically multiplied or divided, it's just some constant. So I could write this as, the rate is K prime, O3 squared over O2. And the reason why we put that prime there is just to note that it is not the rate constant for step 2. This does not equal K2F. Doesn't equal K2F. So we put a little K prime there. All right, try this one on your own and pause the video. I will have the solution up in a moment. Keynote right here. Also, fast EQ means fast equilibrium, which means fast reversible. So it's going to be very similar to the one that I just did. You do it on your own now. There's your answer. Okay, we're going to do one more. You should pause this if you need to check. Okay, one more problem for you to try. I will solve it for you. Pause. All right, we're moving on. Section 12.7, a model for chemical kinetics. So we have something called the collision theory, and there are three things that have to be true in order for a reaction to occur, and this is called the collision theory for reactions. Go ahead and read them. You can pause if you want to. I'm going to move forward. There are some new terms in here. We have activation energy, and I'll show you a graph in a little bit, and I will highlight what activation energy is. But this is the amount of energy the reactants need to have when they collide. They have to overcome that activation energy barrier. So let's look at what we're talking about right here. Reaction pathways, energy diagrams. We are looking at two graphs that are exactly the same. It's just on the one on the right, we're showing you the actual atoms. The one on the left, you're given the chemical formulas. So we have reactants going to products. The distance from the reactants up to the top of the hump is the activation energy for the forward reaction. Up at the top here, we have what's called the transition state or the activated complex. Okay. All right, important notes. On the y-axis, we have the potential energy. That's for both graphs. Again, these are the same plots. They're both energy diagrams. Just one is showing you the atoms. This one showing you atoms. This one showing you the chemicals. All right, quick note, delta H. If you want to find what delta H is, it's the distance from the reactants to the products. That's delta H. Now, you have to think to yourself, is this a endothermic or exothermic reaction? Well, the products have less energy than the reactants. Therefore, this would be an exothermic reaction. So you can always find delta H from these curves. And you have to decide if delta H is going to be positive or negative based on whether the products are below or above the reactants. Okay, so last thing, not last, almost last. You have to know that as the activation energy increases, when you have a larger EA, the reaction is slower because we have a bigger energy that we need to overcome to react, and not enough molecules have that amount of energy. All right, how do we find out what the activation energy is? Well, it turns out there's yet another equation right here. I'm not going to show you how to derive it. This equation is on your equation sheet for AP Chem. We use this equation. K is the rate constant, T is temperature. And we just plot the log of the rate constant versus 1 over temperature, and the slope of the graph right here gives negative EA over R. We set the slope equal to negative EA over R. We plug in the value for R, and we could solve for the activation energy. More important than being able to solve for the activation energy, this equation tells us that the rate constant depends only on temperature, and that's very important. Now for our last thing, catalysts. So this is real quick. This graph shows it to you. The only thing a catalyst does is it lowers the activation energy. So this would be the activation energy with a catalyst. Whereas from here down to here, that is the activation energy without a catalyst. So right here is with a catalyst, this one without a catalyst. The catalyst does not affect delta H. Very important to note. The catalyst does not affect delta H. And that's it.